Good afternoon, bon après-midi. Welcome to this special Physical Society colloquium on the Nobel Prize in Physics. I'm coming to you live from the brutalist majesty of the Rutherford Physics Building at McGill University in beautiful downtown Montreal. I'm here both for the bandwidth, which is supermassive, and of course for the excuse to strut around bedecked in a fashionable martlet face covering. If you are in the Zoom session and you prefer not to be recorded or live streamed, please log out of Zoom and join us via YouTube. This afternoon, we will have a 50-minute talk followed by 15 minutes of questions and answers. To ask a question in Zoom, please use the raise hand feature following the talk. To ask a question in YouTube, please enter it into the chat. The questions will be relayed to me by my sidekick following the talk. Exceptionally, for today's last colloquium of the year, we will not have an après-colloque, and we will have twice the usual number of speakers. With that, I will now pass to Professor Bill Coish to introduce the speakers. Thank you. Notable awards for our speakers today include a number, our speakers today are professors in the Department of Physics, Daryl Haggard and Professor Robert Brandenberger. They both have expertise in the Nobel Prize. Professor Daryl Haggard has received a number of awards. She's a CFAR Azrieli Global Scholar, a Kavli Frontiers Fellow, a CRC Tier 2 in Multi-Messenger Astrophysics. Notably, she received this year, the McGill Principals Prize for Outstanding Emerging Researchers. And she was part of the Event Horizon Telescope collaboration, which was given the 2020 Breakthrough Prize in Fundamental Physics, and of course is a topic of the Nobel Prize. Notable awards for Professor Robert Brandenberger include a Killam Research Fellowship, the CAP CRM Prize in Theoretical and Mathematical Physics in 2011. He is a fellow of the American Physical Society. And in an email to me, he explained to me some of the notable work that he has done with collaborators on work that is connected to this Nobel Prize. He said to me, before Andrea Ghez's work, one of the recipients of the Nobel Prize, we had an alternative explanation for the dark supermassive object, the one that is at the center of the universe, a cosmic string loop. But Andrea's work excludes this possibility. So with that, I will now pass to Professor Robert Brandenberger to begin this adventure to understand the Nobel Prize in Physics 2020. Robert.
Thanks, Bill. Can you hear me?
Yes, we can hear you.
Good. So Bill asked Daryl and myself to tell you something about this year's Nobel Prize. This year's Nobel Prize was awarded for research on black holes.
Robert, could you?
I want to start out with the citations, with the pictures first. So on the left is Roger Penrose, in the middle Andrea Ghez, and on the right Reinhard Genzel.
Robert, would you be able to turn your camera on?
Okay.
Thank you.
Good. So now I read from the citation. So one half of this year's Nobel Prize was awarded to Roger Penrose for the discovery that black hole formation is a robust prediction of the general theory of relativity. Now, the other half of the prize was shared between Andrea Ghez and Reinhard Genzel for the discovery of a supermassive compact object at the center of our galaxy. So at the time when Roger Penrose started working on black holes, which was in the early 1960s, black holes were considered to be exotic solutions of Einstein's equations of space and time without any relevance to the real world, just some mathematical curiosities. Now, in the meantime, black holes have become central both to astronomy, astrophysics, and also to fundamental theory. And I'm going to focus on implications of black holes for fundamental theory and Penrose's contributions, and Daryl will talk about the implications of black holes for astrophysics. So, good. So just to get started, I want to remind you that you could form a black hole, at least a mathematician could form a black hole by imagining that you take the mass of the sun, you take a nice spherically symmetric mass distribution, and you compress it more and more Then space becomes more and more curved at the center point, and eventually space becomes so curved that not even light can escape. Now you can make a little bit more accurate figure by the following space-time sketch. So here the horizontal axis is the distance from the center, and the vertical axis is time. So, and the red curves indicate outgoing light, the blue curves indicate ingoing light. And as you see from this diagram, as you slowly approach the center, these light cones get deformed. And eventually, once you pass this distance, which for this particular mathematical solution is 3, then both ingoing and outgoing light is inward directed. So that's a bit strange that you have light going in direction of negative r, light going in direction of negative r. So somehow these coordinates are not very good coordinates, and we'll come back to that. So this is a black hole, and black holes have a huge role in astrophysics. This is just a preview of what Garo will talk about. Black holes form as a final stage of the collapse of high mass stars. Black holes seed type 2 supernova. Gravitational waves from binary black hole mergers have actually been observed. And then there are these supermassive black holes which reside in the centers of galaxies. However, my role today is to talk about theoretical implications of black holes. And I want to start out with the second law of black hole thermodynamics, which was proposed by Bekenstein and Hawking at the beginning of the 1970s. So if you look at classical general relativity, then you can prove that the area of this black hole horizon, let me go back. This is the black hole horizon, where you see my cursor. So the area of this black hole horizon is a non-decreasing function of time, like the entropy is a non-decreasing function of time. And therefore it was postulated that black holes have entropy, which is proportional to the area of the horizon, Now, if this analogy is to be better than a formal analogy, then, well, objects with entropy should radiate. But classically, nothing can escape a black hole. However, Hawking in 1974 was able to show that if you include quantum effects at the semi-classical level, then you find that black holes emit thermal radiation with a temperature which is inversely proportional to the mass. So the mass will decrease and the black hole decays in a finite amount of time. So now let me come to the first time that I mentioned Penrose's name. So Penrose and Carter, they constructed better coordinates to describe a black hole. Coordinates in terms of which light always travels at 45 degrees. And also in which infinity is brought into a finite value. So in this diagram, this region, which I'm showing you now with my cursor, is the outside of the black hole, the outside of the horizon. This is past infinity. This is future infinity. And from this diagram, you see that an observer who's venturing into the black hole, towards a black hole, will cross the horizon without any trouble. But then, well, according to Einstein's theory, there's a singularity at the center of the black hole, which is bad news for the traveler. So now this black hole solution was constructed with very symmetric initial conditions. Spherical symmetry was assumed. Okay, but I'll come to that. Now, Hawking realized that black holes will evaporate. So therefore, the space-time diagram of a real black hole will look rather different from what I just showed you. So here I'm actually showing you the space-time diagram of a star that collapses to form a black hole. The black hole evaporates, leaves nothing behind except for radiation. So R equals 0, that's the center. This A semicircle indicates the surface of the mass which is collapsing. At a certain time, the horizon forms, the black hole starts to radiate, eventually the black hole decays, and you're left with something that looks like flat space. So this is the Penrose diagram of an evaporating black hole. And you see, now you have a problem. So if you imagine throwing a copy of Encyclopedia Britannica with all its information into the black hole, and you wait until the black hole has decayed by emitting thermal radiation, then you have a problem. Either information is lost, which means that bad news for quantum mechanics apply to this situation, or else information is preserved, unitarity is preserved. In that case, there's some process which means that Hawking radiation is not perfectly thermal, or else you get a remnant. Now, initially there was a lot of disagreement between these three options, but I think now it's quite clear that unitarity is preserved, quantum mechanics works, but we still do not know exactly how the information is emitted. So key issues for fundamental gravity, for fundamental physics, include how is information maintained during black hole evaporation? Holography plays a crucial role in quantum gravity. So if you try to quantize gravity without taking into account black holes, then you will definitely fail, as Lenny Susskind explained to us last week. And also, if you try to believe that field theory will work in the extreme ultraviolet, this will also inevitably break down. This is motivation for some of my work on the trans-Planckian cosmic censorship hypothesis. So where does Penrose fit in? So let me start with one slide on Penrose's life. So he was born in Britain, and he actually spent World War II in Canada, where his father, who was a psychologist with mathematics training, was teaching or doing research. After returning to England, Penrose enrolled in University College London, where his father was teaching, and he obtained a bachelor's degree in mathematics. He then moved on to Cambridge, where he again joined the mathematics department and got his PhD in algebraic geometry. After getting his PhD, he stayed in Cambridge as a research fellow. Part of the time he spent on a research fellowship at Princeton and Syracuse. On his return to England, he became a researcher at King's College, then a reader at Birkbeck College, a professor at Birkbeck College, and eventually the Rouse Ball Professor of Mathematics at Oxford. And he's still at Oxford. So it is during his time in Cambridge that Penrose started thinking about the issues for which he was awarded the Nobel Prize. And let me put this research into historical context. So at that time, general relativity was considered to be a branch of applied mathematics. Astronomers didn't study it, physicists didn't study it either. Black hole singularities were considered to be a feature of the special spherical symmetry, which Schwarzschild assumed when he derived the solution. So you can see that if you imagine focusing matter at one point, it's easy to imagine that you get a singularity. And it's also easy to imagine that if you destroy the symmetry, if you had a little bit of angular momentum or a little bit of asymmetry, then you won't focus matter to one point, and then you might avoid the singularity. So now there's also cosmology. Big Bang cosmology was a pejorative term. The dogma was steady state cosmology. But among mathematicians, there was growing interest in mathematical aspects of general relativity because the equations of general relativity are rather complicated and interesting. But then there was something special because quasars had been discovered. And there was a hypothesis that quasars are powered by a supermassive black hole. Now, the person who was key to Penrose in Penrose's Cambridge days was Dennis Sciama. Dennis Sciama was one of the rare people at that time who had both expertise in astrophysics and in general relativity. And in the Cambridge College atmosphere, Penrose met people who were not pure mathematicians. He met physicists, he met Sciama, and he was intrigued by black holes. And in particular, Penrose was intrigued by the question of whether you change the distribution of matter. You don't just have spherical symmetric matter. You allow some angular momentum, some asymmetry. Do you still get the singularity? In fact, Penrose proved that black hole singularities are generic. And so there'll be two technical slides. And now comes the first one. So Penrose's 1965 paper said the following. So let's consider collapsing matter in a space-time which is flat at infinity. And let's assume that Einstein's equations hold. Let's assume that the energy density of matter is positive. And let's assume that matter is infalling. And let's assume that time doesn't end in the future at finite time for the observer at infinity. So these are some translation of these technical words. Then Penrose proved that the manifold must be singular. So the black hole singularity is generic. So at the same time when Penrose published this paper, Sciama had a student, a young student, Stephen Hawking. And Stephen Hawking set out to generalize Penrose's work, in particular to cosmology. And in the years between 1966 and 69, Hawking made lots of breakthroughs. And this work on singularity theorems culminated in a joint paper by Hawking and Penrose in 1970, published in the Royal Society, London, submitted by Hermann Bondi. And the title is Singularities in Both Gravitational Collapse and Cosmology. And this is the second technical slide. The theorem is, assume that space-time is described by Einstein's equations and assume that the cosmological constant is not positive. Assume that you can't go forwards in time and kill your grandfather. And now you have to assume some conditions on matter, not just the energy density, but also the pressure. And these, for ordinary matter, these are trivially satisfied. And then there's another technical assumption about trapped sets. In that case, Hawking and Penrose proved that space-time is incomplete. So you can travel back, you can follow light rays either forwards or backwards, and you find that these light rays end at finite travel time. So it means a singularity. And the corollary is that given an expanding universe today, then there was a singularity in the past. So these theorems attracted a lot of attention, and Penrose and Hawking got lots of prizes for that. So, and the impact of the work was important because in that period, there were lots of discoveries. The microwave background was discovered. Peebles established standard Big Bang cosmology. And then there were all these astrophysical discoveries, which Daryl will talk about. So there was growing interest in relativity, black holes, and cosmology. And Penrose's work really inaugurated the golden age of research in classical general relativity. So Penrose made other contributions. So one contribution I already mentioned, namely these diagrams with which to depict space-times in a way which makes causality manifest. This was work by both Carter and Penrose. And then, so it's diagrams like this. And Penrose also postulated a cosmic censorship conjecture. This is still a conjecture, and the statement of this conjecture is the following. Einstein's equations permit strange solutions where the charge is bigger than the mass. And in those solutions, the singularity is not hidden from us by a horizon. And what Penrose postulated is that the full physics prohibits to have these pathological solutions. This is my rendition of the cosmic censorship conjecture. And again, this cosmic censorship conjecture is key to research I've done just in the past year on what we call the Transplanckian censorship conjecture. Now, something else which all astrophysicists know about is the Penrose process. So for rotating black holes, you can extract energy from the rotation of a black hole in the following way. You send a particle into this ergosphere, it scatters off of a second particle. There's one outgoing particle which emerges with more energy than the incoming particle. So the Penrose process is something important. Now, Penrose, in a similar time period, made other important contributions to gravity. He invented twistor theory, and he invented spin networks. So both twistor theory and spin networks at a certain period of time were thought to be important for quantum gravity. But Penrose was actually a mathematician by training, and his father was both a psychologist and a mathematician. And when Penrose was a student, he published a paper with his father in the British Journal of Psychology, in which he discussed this object, which is now called the Penrose triangle. So this is a triangle, but if you look at this triangle, you think that each angle is 90 degrees. It's obviously an illusion. So this is a Penrose triangle. And then the other discovery which made Penrose famous is these Penrose tilings, which now have a physical realization in terms of quasicrystals. Okay, so all of these breakthroughs of Penrose, which I mentioned, were in the period before 1980. But Penrose remained active since then. But in my opinion, he's become a little bit of a maverick. So let me be a little bit careful here. So he, in a period between 1980 and the present time, he's published a lot of articles. He's published a lot of books, popular science books like The Emperor's New Mind. He's explored many ideas, unorthodox ideas about cosmology, about consciousness, and about the foundations of quantum mechanics. But all of these ideas have actually been quite heavily criticized. So I will leave you with this picture of Penrose, the way that I actually met him when I first met him at a conference in India. And I'll hand it over to Daryl.
Thank you very much, Professor Brandenberger. You're actually 5 minutes early, but that's fantastic. We'll have more time for questions. Please keep your questions handy and get them ready for after the talk from Professor Haggard, and then we'll have questions from both the speakers.
So I will stop sharing the screen.
Thank you. Daryl, can you share your screen?
Yes. How is that?
Looks good.
Great. Okay. Thank you so much, Robert. So I'll cover a little bit of the same kind of intro material that Robert did, at least in a couple of places. So let me just say thanks to everybody for being here. And I just want to emphasize, as Robert has also done, that this is a really exciting domain to be working in, and there's a lot of very rapid discovery happening. And I'm going to emphasize that just in the form of a couple of different highlights over just the last couple of years. So we had this amazing Nobel Prize a few years ago in 2017 for the first discovery of gravitational waves, another black hole discovery. And I put a fun quote here from Ray Weiss: every day is an interesting day. And some of you may be begging to differ a little bit right now in our COVID times. Some days feel a little less interesting than others. And then we had an amazing neutron star merger that was detected via gravitational waves and other messengers. and the detection, the first sort of image of a supermassive black hole. And then this year, this incredible Nobel Prize for these three fantastic scientists, Roger Penrose, Reinhard Genzel, and Andrea Ghez. And I'll talk a little bit more about the movie you're seeing now in just a minute, but Robert has told you quite a bit about Roger Penrose, and I'm going to spend my time focused on the science that Reinhard Genzel and Andrea Ghez have offered and were awarded the Nobel Prize for. And I'll just read Andrea Getz's quote from the sort of initial announcement of this discovery. She said, "I hope I can inspire other young women into the field. It's a field that has so many pleasures, and if you're passionate about science, there's so much that can be done."
But before we go too far, are we going to do the poll now, or?
Yes, right now. Thank you,
Okay,
Bill.
sorry.
So Bill has been incredibly kind and helped me set up a poll for all of you. And so Robert has given you a little bit of thinking already about black holes, and I wanted to do a Zoom poll because here we are at the end of the term, and who hasn't enjoyed Zoom polling this term? So if you can go for it, I have 2 questions in my Zoom poll, and I'd love it if people would just toss in their answers.
Okay, I'll launch the first question now.
Great. So the question then to everyone to start off is, which of the following do you consider the most compelling evidence for black holes? And your options are radio detections of quasars and AGN, X-ray detections of black hole accretion flows, the S-star orbits around Sagittarius A star, the LIGO-Virgo detection of gravitational waves from black hole mergers, the Event Horizon Telescope image of M87's black hole shadow, all of the above or none of the above. And for people that don't know what all of these different observations are, that's totally fine. You can just, throw a dart at the wall and see what you think. So we'll just give it a few minutes for people to vote. And if you've already finished voting, let me anticipate a little here. So you can vote on both of these 2 questions at the same time. So down in the second one, which of the following do you think offers a legitimate test of general relativity? The precession of Mercury's orbit around the sun, gravitational lensing, again, the S-star orbits, which you're seeing here in the video behind on the screen. LIGO-Virgo detection from gravitational waves from black hole mergers, EHT, all of the above, none of the above. So, to spend a couple minutes more here, I can see lots of numbers streaming in, and then Bill can, in just a minute or 2, share your opinions back with you. I tried to do this a few weeks ago at the Princeton Institute for Advanced Study colloquium that I gave, and they weren't as snazzy as Bill, and we couldn't get the Zoom poll set up. So I have those just as a chat info, but it'll be fun to compare how you all think.
So we have a 72% response rate, but I think we can get it to 80%. Please, let's get going.
Vote your heart out, people. So we can reach our 80%, just like we all want to reach on all of our course evals. Another 5%.
Okay, it's slowed down a bit. So I think
close, 77, 78.
Oh, almost there.
Oh, almost there. Oh, 79. Two more people, 3 more people. So close, so close. Okay, let's close the poll and see. We almost, rounding errors. I'm an astronomer, 80%, pretty close. So it looks like we have, hopefully everybody can see the poll. I can. So people are sort of split between the S-star orbits, LIGO, Virgo, and the Event Horizon Telescope, or all of the above. I think maybe got the most votes for our first question. In our second question, folks basically liked all of the above too. So this is good. Some of you are slightly less skeptical than colleagues of mine who think none of the above might be the better response, at least to the second question. But thank you for doing a little poll. Thank you, Bill, for coordinating that with me. And I'm going to talk mostly here about the S-star orbits around Sagittarius A star, which are the incredible contribution from Andrea Ghez and Reinhard Genzel. So moving on here, let me just mention that Andrea Ghez also was our McPherson lecturer in 2013. So Robert reminded me of this just before we joined you all on Zoom. So we were lucky enough to hear a talk from her not so many years ago here at McGill. She's been an inspiration to many of us in the North American astronomical community for a long time. So Robert's given you a sophisticated sort of look at what some theorists think about for a black hole. As an observer, I am a little bit more sort of focused on just the observables in the universe. And so two of the things that you can observe about a black hole are the mass and the spin. And the mass is really sort of a controlling factor. And the thing that I think really kind of pinned down this Nobel Prize winning research that, that Reinhard Genzel and Andrea Ghez were awarded the prize for this year. Spin is actually very important and interesting also for black holes. It's a lot harder to constrain observationally. And so I'm not going to talk about spin really today, but there are many different studies that are underway to try to observationally constrain the spin. But we're really going to think mostly about the mass of the supermassive black hole in our Milky Way galaxy. And so Robert discussed this as a sort of a singularity. This is this extraordinarily dense mass inside of a Schwarzschild radius or an event horizon, as the Star Trek community has sort of helped popularize the notion. And so what we are seeing here is an extraordinarily dense body for which we can't actually constrain the conditions of the matter inside of the Schwarzschild radius. So the Schwarzschild radius, sort of simply explained, is just where you take an escape velocity for a body and you equate that escape velocity to the speed of light, meaning that information, as Robert has explained, is sort of trapped inside of some radius. So even though the density of this black hole may be infinity down here in the center, our observable region, it actually lies just outside of this Schwarzschild radius. So you all can calculate the Schwarzschild radius very easily. You just equate, this is kinetic energy, potential energy, you solve for velocity, set that equal to the speed of light. And that allows you to determine the Schwarzschild radius. And you'll notice that the Schwarzschild radius is only a function of mass. And this is one of the reasons that the mass of the black hole is such an important feature when we're trying to understand how to go out and look at black holes to make observations of the conditions around the black hole. And we're really, when we talk about seeing a black hole or observing a black hole, what we're trying to look at is material that's in the vicinity of this Schwarzschild radius and the vicinity of this event horizon. And that can allow us to constrain a certain amount of mass to within the Schwarzschild radius. If we're seeing the bulk of that mass outside of the Schwarzschild radius, that would not be a black hole. But if we can say the object must be within this event horizon, then we can start to think about it in terms of a black hole or black hole astrophysics. And anything everything has a Schwarzschild radius. You have a Schwarzschild radius. Your cell phone has a Schwarzschild radius. But astrophysically, of course, we're really interested in these bodies that you've seen in some of the pictures. So one of the most impressive images we've seen in the last year or two is this beautiful image of M87. So this is a black hole that has 6.5 billion times the mass of the sun. Its event horizon is inside of this very, very hot material that we observe around the outside of the event horizon. And just to put that in perspective, this is 6.5 billion times the mass of our sun inside of something that is sort of roughly the size of our solar system. So you can see XKCD has made us a nice little sort of picture of what Pluto's orbit would look like superposed on this supermassive black hole. And this is the Voyager mission, which is the most distant satellite we've ever sent away from our Earth. So you can imagine if we lived, in the vicinity of this black hole, we'd still barely have managed to, even if we could get out, we'd barely have managed to look at the edge of our black hole event horizon. Of course, our we can also think of this in terms of another object. So our Earth is, 3 millionths of the mass of the sun, but it can have an event horizon too, and we can figure out what its Schwarzschild radius is. And if you figure out the Schwarzschild radius for our whole Earth, it's something like that of a sugar cube or a rolling die. And so anything can be described in terms of its Schwarzschild radius because this is simply a very simplistic metric which is based entirely on mass. Okay, so Robert mentioned we've got two different classes of black holes. I mentioned these in part because the stellar mass black holes, which we think are the black holes that are left behind after stellar explosions, in supernovae, have masses something like 10, sometimes up to something like 1,000, 100, maybe 1,000 times the mass of our sun. And these black holes, these smaller black holes, were predicted by our models of stellar evolution. So when people thought deeply about what would happen to a massive star and thought about how that evolution would proceed after it ran out of hydrogen in its core and could no longer support hydrostatic equilibrium, people thought that these objects, these massive stars, ones that had 10, 10, 20, 30 times the mass of our sun would end as remnants that were black holes. And so this was a prediction that then people went out and tried to measure, the observables that might lead to a better understanding of these black holes. The opposite is true in the case of supermassive black holes. And Robert already anticipated this a bit in his discussion of Penrose, that Penrose was really challenged and thinking about supermassive black holes because of the discovery of these objects known as active galactic nuclei. Active galactic nuclei, I'll show you some of these really spectacular pictures. These were really first sort of explored mostly at radio wavelengths because they are very, very bright due to their synchrotron radiation, electrons spiraling along magnetic fields. And these incredible bubbles of radio emission that seem to be emanating, the energy seems to be coming from this tiny, tiny, tiny little core, puzzled people and really challenged theorists to start thinking deeply about how a little object that was so tiny and so small, even in the context of its own host galaxy, could generate this enormous amount of energy. And so really the beautiful observations of active galactic nuclei, which we just call AGN, or sometimes quasars when they're very bright, really pushed theorists to be thinking about how supermassive black holes could form and how they might impact their environments and the galaxies that they formed in. This is another beautiful example of this. This is M87, the same one that I showed you a minute ago. And you're seeing here now marching out from the event horizon, the base of the jet, the origin of the jet, and then the jet on extraordinarily large size scales here in this beautiful galaxy at radio wavelengths. And then you're also seeing this same jet mapped out here at higher energies at X-ray wavelengths. And so this is a lot of the work that I do, but this is a galaxy that is about 100 times further away. It's at the heart of the Virgo galaxy cluster, 100 times further away than our most local supermassive black hole. And it's this local supermassive black hole, which we pet name Sagittarius A star, that Andrea Ghez and Reinhard Genzel are really credited with understanding very, very deeply and really constraining in terms of volume, really pushing down toward that short shield radius, toward that event horizon, to constrain the mass to an extraordinarily small volume and really conclusively show us that observations could reveal a supermassive black hole. So this is a really beautiful diagram that my colleague and friend Betsy Mills made, starting out at very large scales. So this is 100 parsecs. A parsec, for those of you that don't think in astronomy units, is something like 3 light years, very roughly. So 100 parsecs here. This is sort of, a size scale that is fairly large, but really still confined to the center of our Milky Way galaxy. If you were to look at the band of light that is the stars you normally associate with the Milky Way galaxy, it would run this way through this image. If you zoom in on this very kind of interesting looking region here, you can see all these purple lines are helping trace out magnetic fields in the center of our galaxy. If you zoom into something more like 7 parsecs, you see now there's this very large structure. This is actually a supernova remnant. Off on the edge of the supernova remnant is this interesting additional feature, this sort of swirly looking feature. We call this the circumnuclear disk. This is now a 3 parsec scale. Inside of there is actually a mini spiral. Marching in a little bit more, we start to be able to map out the central light year, and you might be able to barely see a fuzzy little arrow pointing into the middle of that box. Down in the middle of this box in the central light year are those S stars. I showed you that movie on that first slide. These are the star cluster that is in the vicinity of the black hole, Sagittarius A star, that has allowed us to really map out and to march down in toward that short shield radius and confine the mass of the supermassive body that's in the center of our own Milky Way galaxy. So this is a really cool image, in part because each one of these different size scales is actually mapped out by observations, by data, and that's really a spectacular accomplishment by itself. So in here, this is known as the S star cluster down within the central light year. This is actually a beautiful map of many of those S stars by Stefan Gillison, who's a member of the team in Germany, Reinhard Genzel's team. These stars are very interesting. They're in bound orbits. They're very young stars, and that's important because it means they're extraordinarily bright so that we can see them, even though we have to peer through all of the muck of our own Milky Way galaxy. And because so many of them are so close to the black hole in the center of the Milky Way, they really help us probe out its gravitational potential well and help us understand where that mass is located and how much mass it is. So these S stars, if we zoom way in, we can actually see that individual sources are very close together. They present quite a challenge because these stars are orbiting around a massive object and they blend together and overlap one another and have been monitored now for more than 20 years in order to really get those amazing kind of movies that we can see of the galactic center. So here's how we understand and constrain the mass of the supermassive black hole. So this is a series of orbits of those S stars in the galactic center. You can see here that these have been mapped out for many, many years. I'll show you some even more up-to-date information in just a minute. And each one of these different stars is actually on a very close to Newtonian orbit around the supermassive black hole. You can see that they all have the same point as the focus of their orbits. And we can figure out the mass enclosed by looking at their orbits and tracing them over time. You can see here now on this side is the enclosed mass as a function of the distance from Sagittarius A star. And the hope here, of course, is that you can march down very far along this sort of radius and get extremely close to that event horizon with your stellar orbits in order to constrain the mass enclosed within a very, very small volume in order to conclusively say that you're looking at a supermassive black hole. And so this work has been done, as I mentioned, by two different competing teams. So Reinhard Genzel's team at the Max Planck Institute for Extraterrestrial Physics has been pursuing this for about 20, 25 years, as has Andrea Ghez at the University of California at Los Angeles. And these two teams use different observatories and different instruments to do this work. This means that they're rather fierce competitors, but also that they really challenge one another and that they are pushing on the technology constantly to do a better and better job of making these measurements. And so I think this has really kept it a very vibrant exploration, and the two teams are seeing much of the same phenomena. So this is the kind of current state of the art for traces of these S stars in orbit around the supermassive black hole, which is marked out by this white star here. You might notice if you look very closely that some of these lines are dashed at the beginning of the animation and they become solid as you go later into the animation. That actually represents an enormous step forward in our technology for being able to look at these stars in the galactic center. The dashed lines are showing you the positions that we've figured out for those individual stars using imaging only. When they become solid, that's when we start to be able to collect spectroscopic information in order to get radial velocity motions in addition to motions in the plane of the sky. So now instead of having only a 2D approximation for these orbits, we can get a fully realized three-dimensional solution for the orbits of the stars. And that's very, very important if you want to figure out exactly what your reference frame is and exactly how these motions are evolving over time. If you hear Andrea Ghez talk about this, this set of observations, she'll always highlight for you the star that is highlighted here at the end of this animation. These observations were taken, you'll see in 2020, they were taken this year. And this star, SO2, I'll play the movie one more time, keep your eyes on this yellow trajectory. You'll see that this star actually has an orbit, its orbital period is around 15 years, and it makes more than one orbit over the course of the time that we've monitored this star. And this means that the orbital solution is really, really, really accurate at this point. It also means it's valuable for trying to look for GR effects like precession in the orbit and other very interesting tests of general relativity. And so this star SO2 here is the one that you'll find these two teams really kind of obsessively pursuing in a lot of their observations. So I want to show you a little bit just what the actual data looks like. So that little rainbow plot is fun, but it's kind of cool to see what you actually look at when you look at, the galactic center with an observatory. And so you'll see that these are showing you little videos, little different wavelengths of data spanning over several years. And you can see here the stars actually being traced out. There's quite a lot of jiggle in these observations. It's not as easy as it might seem when you see it all as like a pretty rainbow picture. But so Andrea Ghez, and actually if you move my little picture here, you'll see Andrea Ghez is actually up in the upper right hand corner. this is a little snapshot borrowed from a talk that she gave for the Maria Gephardt-Mayer Prize lecture at Chicago just after winning the Nobel Prize this year. She'll tell you that before these long-term sort of 20-year baselines for monitoring the stars in the galactic center, this circle is representing the area within which we knew there had to be 4 million times the mass of the sun. But we didn't know exactly how concentrated that mass was. And as you can see, there's a lot of stuff in this radius. And so it really is the monitoring of these stellar orbits that allowed us to move from an understanding that just showed us, you know, a whole bunch of stuff and in some area within which there had to be a whole lot of mass, to being able to really move down through size scales, which are equivalent to like marching in toward our own sun in our solar system, which would fit roughly within this circle, to being able to constrain those 4 million times the mass of the sun to something that is more like the scale of the sun itself in our solar system. And so this is something like a 10 million times smaller volume than we started out with at the beginning of these studies 20 some odd years ago.
You have about 5 minutes left.
Thank you very much. Okay, and so how did she do this? How did she and Reinhard Genzel, using these two amazing observatories that you're seeing here? I want to just talk very briefly about the technology. So, and in particular, remember we are seeing in that video those stellar orbits that were dashed and then that became solid. And I said that was a real advance in technology. And so how did that happen? So the thing that happened, the technological step forward, was this technique known as adaptive optics, which is just really super awesome and we could talk about for a long time. But adaptive optics is basically a technique where you take these lasers. These are not photoshopped. These are actual lasers beaming out of these observatories. So this is the Very Large Telescope down in Chile, the one used by the Max Planck group. This is the Keck, the twin Keck telescopes at Mauna Kea. Used by the UCLA group, and you can see that they're shining these crazy bright lasers up into space. So why do that? So it turns out that one of the real challenges of looking toward the galactic center is that the light coming from objects, actually this is true of all objects in space, it travels to us relatively unimpeded, but then just before it reaches our observatories, it hits the upper atmosphere. And our atmosphere is moving like crazy, and it makes all of that light get spread out, and we can no longer carefully pinpoint sources. And that means that our resolution, if we want to pick out individual stars and follow their orbits over time, is really disrupted by this twinkling, right? We call it that you want to take the twinkle out of the stars because we're mean astronomers. And so Andrea Ghez will tell you, and if you hear her talk about these things, you know that this light from the galactic center traveled to us unimpeded for 26,000 years. And in the last 30 microseconds, the atmosphere completely messes it up. So the adaptive optics is here to try to help us undo that. You send a laser out from a very high powered sodium laser out from your observatory. That laser goes out and excites a layer of sodium up at about 90 kilometers in our upper atmosphere and makes a very bright fake star. So that sodium laser is actually interacting with tiny little sodium atoms that have been deposited in the upper atmosphere by micrometeorites as they rain down on our Earth. And so this is like super cool. And these lasers make this fake guide star, and they allow these telescopes to actually slowly adjust or rapidly adjust their mirrors to undo the twinkling of the atmosphere. And so I have a movie, but I won't have time to show you, but it's basically, it acts as sort of a wavefront center that allows you to bend and slightly adjust your mirrors, kind of like a funhouse mirror, but then you want the exact opposite of that to unbend your wavefront so that they come in smooth and nicely focused at your observatory. So this adaptive optics was something that scientists were working on really, really actively. And then we made a huge leap forward to the 90s because the military, of course, does this in the other direction. And they had all sorts of really fantastic technology. And the scientists were catching up so quickly that they finally were like, okay, fine. And they just declassified it. And so all the scientists and the military scientists came together and really refined these techniques very, very rapidly in the 90s. And this adaptive optics technique is actually been really successfully used to help refine LASIK eye surgery. All this wavefront sensing and correction has actually been really interesting across a lot of fields of detectors and other areas, not just astrophysics. All right, so this is adaptive optics off, and this is adaptive optics turned on. And hopefully you can see just by looking at this one image that in the era before we had adaptive optics, it was really, really hard to see stars that were very, very close to Sagittarius star, let alone trace out their orbits. But once you have this adaptive optic techniques giving you this really beautiful high resolution imaging and eventually spectroscopy, now you can actually really trace out those orbits way down toward that event horizon, which is your goal. Okay, so I'm gonna skip over the video, but we can come back to it. And just make one last point. So these are the spectra. This is SO2 as it goes around. This is its spectra. So for anybody that's looked at astronomical spectroscopy before, here's an absorption feature. This is 2018, 2018, 2018, 2018. This is, sorry, it should go the other way. 2017, March, April, May, July, and you can see here that this line is the same absorption line as the star goes into periaps and then, or closest approach to the black hole, and then comes back out of it again. So that's as the star is basically whipping around here. You're actually seeing the red shift of this one line, the Doppler shift of this one line cruising right by. And so one interesting test of GR, and then I'll wrap up, we can actually use this because the star SO2, so this is the orbit of SO2 and this is its spectrum over time, because it comes so close to the black hole, there's actually a little bit of gravitational redshift in this spectrum that we're seeing as well. There's the Doppler shift and there's also a little bit of gravitational redshift. And this was beautifully detected by both teams just this last year. This line down here in the blue dashed part of the figure would be just Newtonian gravity if you had no GR, if you had no gravitational redshift in this spectrum that you're seeing at all. And this is the deviation away from that as predicted by general relativity, by this extra gravitational redshift you get as the star falls into the potential well of the supermassive black hole and then comes back out again. And you can see here the data points are beautifully fit to this model. There's a very, very clear detection by both, again, by both the UCLA and Max Planck teams of this deviation from Newtonian physics and a real confirmation of GR in the strong gravity regime, right? So we have LIGO and Virgo, and they've taught us a lot about GR and what it can help, tests of GR in the lower mass regime of lower mass black holes. And we're seeing beautiful confirmation of that same theory here in the vicinity of a supermassive black hole, which is awesome. Okay, so I'll just stop here with, this is an exciting field and we're doing all sorts of cool things. The Event Horizon Telescope will observe Sagittarius star and give us some other interesting measures. And for the work that Andrea Ghez and Reinhard Genzel are doing, one of the things that people are really hoping to do is get bigger mirrors and to be able to go from this configuration where we are now. A next generation of adaptive optics might get us here, but an even larger telescope might get us here. And now you're really looking at many, 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 many stars, fainter stars, more numerous stars that are very, very close to the supermassive black hole and allow many, many multiple tests of general relativity, of the mass of the black hole, of all sorts of other interesting things about the stellar population in the galactic center. So that's exciting. We also have more observatories coming on down the line always to try to understand the environment of this supermassive black hole and its variability and a lot of other things. And then just before this colloquium, I was listening to another talk by Andrea Ghez for the Event Horizon Telescope collaboration. I will just share her conclusion slide with all of you. And so this is Andrea's slide. And she says that this Nobel Prize is acknowledging the discovery or confirmation really that our galaxy harbors a 4 × 10⁶ stellar mass black hole. And that these amazing stellar orbits that she and Reinhard and others have worked on improves the case for a supermassive black hole by a factor of 10 million, which is really enough precision now to confirm that supermassive black holes exist. And we think that most, if not all, galaxies harbor a central black hole. And so there are also these other fun, many, many, many exciting future tests that these data will be able to help us work on as we go forward too. That's it. Thanks.
Thank you very much, Professor Haggard, and thank you, Professor Brandenberger, for 2 excellent talks, or 1 excellent combined talk, I think. If you appreciated the talks, please say so in the Zoom chat or on YouTube. If you're on YouTube, please say something in the chat. And now is time for questions. So Robert, could you please unmute yourself? I will switch the speaker view, which is good. Once the chatter in the chat on Zoom dies down, if you would prefer to ask a question anonymously, please feel free to type it into the Zoom chat. I'll try to read it out for our speakers. Otherwise, if you would like to ask a question in your own words, please use the raise hand feature in Zoom. And I'm sure there will be questions. There is one already from Professor Jim Klein. Jim, please unmute yourself and ask your question. Oh, you will not be able to because I haven't allowed it. I'll allow you to unmute yourself. You're now allowed. Could you please unmute yourself and ask your question? Turn on your video if you like. Jim?
Sorry, I kept clicking and kept getting nothing, but thanks for that nice talk, Daryl. I just wondered, what are the right answers for the poll?
There are no right answers. No, I kind of agree with the all of the above, but I will say, so the tests of GR are really controversial. I don't think we've actually made a convincing test yet for the precession of SO2's orbit in the galactic center. But I do think that that last result I was showing you, that really strong detection of gravitational redshift is a very nice step toward actually being able to test GR with the S stars in the galactic center. And I think that there has been a very, very lively debate between Event Horizon Telescope collaboration folks and folks outside of the collaboration about whether or not the observations of M87, that black hole image from the Event Horizon Telescope collaboration, whether that is truly a test of GR. And I think there's a lot of reason to be careful about these things because astrophysics is a really messy. There's a lot of things that you have to correct for, and that includes everything from like dust extinction to understanding your reference frame for these S-star orbits in particular, understanding a lot of the sort of astronomical sources of error. And it turns out, I did not actually realize until just the last 6 months, there's a paper by Gralla that has kind of taken aim at those EHT results and whether or not the GR tests are robust. And then there's been a ton of conversation back. So I think if you're curious to see how people are thinking that it may not really be a completely robust test of GR and how the rebuttal is going to get worked out, those will both be out on AstroPH within the next couple of weeks. And so I think that all of these are really incredible tests, at least of the existence of black holes. I think many of those are incredible. LIGO Virgo is incredible. So I'm kind of on the optimist side. I'm on the glass half full side of both of those polls.
Thank you.
Okay, thanks for the question. There's another question that appeared in the Zoom chat, and it's the same question that I asked the two of you by email. So I think it's for both of you, whoever wants to answer, or maybe you can collaborate on an answer to the question. The question starts, amazing talk, thank you. The motions of the stars of the Sagittarius A-star cluster are incredibly convincing. You seem to suggest some people still don't accept it as a proof of black holes. What are their arguments? So Daryl or Robert or both of you?
This is a question for Daryl because you see, I'm persuaded. And the reason I'm persuaded is that the alternative model, which I thought of, has been excluded because we now probe so close to the center. And this alternative model would have predicted deviations from what we've now seen. So I am persuaded.
Yeah, I think people are becoming increasingly persuaded. And just to reiterate, I think the argument that Robert already offered, one of the alternative possibilities is that instead of a single monolithic supermassive black hole, you had a sort of a hive or a cluster of black holes. And as you probe in closer and closer and closer to that central mass, you constrain mass exterior to your probe more and more convincingly. And so as you come down in very close to the black hole, you start to be able to rule out, say, a hive of littler black holes or some other mass. You would start to see a turnover, right? You'd start to see that you've moved inside to the interior of that mass distribution. And so I think that Robert's right that as those constraints have come closer and closer and closer to the black hole, they become kind of more and more convincing that there's really a supermassive black hole there. I will say, and Robert will probably have some additional thoughts about this, we still don't have a completely coherent and cohesive argument for how you form black holes and supermassive black holes, I mean, not black holes in general, and in particular, how you form them so early in the universe. And so people are still very interested in black hole formation, supermassive black hole formation, and the co-evolution of supermassive black holes and their galaxies. So there's a lot of active ongoing thinking and research about that question. I think maybe we lost Bill. So Jim, I don't know whether you had another question, but I see also Adrian's hand is up. Maybe Adrian, we can just call on you ourselves.
Hi, no problem. Thank you both for the talk. I have a question related to the S stars. So you mentioned, Daryl, that in order to track them, you also have to take into consideration the reference frame. So I was actually a bit interested in that. What are the technical issues with actually tracking what the point of focus is for their orbit? And is the supermassive black hole also undergoing its own motion and dynamics when you take that into consideration?
Yeah, so if I understand correctly, and because these are not my observations, so if I understand correctly, the major challenge is actually that how well you can constrain the shapes of the orbits. So remember, what you're trying to come up with is a full 3D, time-dependent 3D position for each of those stars in the galactic center. And so if you don't fully understand the shape of the orbit, you can slightly get wrong what your reference frame is. And so you try to build up a more and more convincing geometry for the whole system by having multiple stars. But as you could see, we only have one that has completely closed its orbit. And so that particular star, we have the best sense of what the shape of its orbit is. But for the other stars, we don't have as much confidence. And so that will come with longer observations and more time. And as we do better at constraining the shapes of the orbits, we will do better and better at identifying what the reference frame actually looks like. So it's like a sticky kind of technical issue. And as for a proper motion, I don't know. I think that also is possible. We don't think it's moving around a lot, but we see a lot of evidence for other supermassive black holes sloshing in their gravitational potential wells. And so certainly that is an important consideration for many black hole studies. It doesn't seem to be a huge factor for Sagittarius star in our own galaxy.
Thank you very much.
Okay, I had a little technical difficulty, but it seems I'm back online, kind of. So I guess I can call on the next person. I see that Hassan Badami, would you like to unmute yourself and ask a question?
Greetings, can you hear me?
Yes, we can hear you.
Thank you both for the great speeches, and I'm an undergraduate student, so pardon my simple questions. In the first lecture, you mentioned the second law of thermodynamics for a black hole, that the entropy of a black hole is proportional to the area of the black hole and not the volume. And it made me wonder, does this confirm the holographic models?
This is in support of the holographic models. In fact, the holographic approach to quantum gravity is very much influenced by this second law of black hole thermodynamics.
And another question is that what is a basic amount of the entropy of a black hole? I mean, what fraction of the entropy of the universe does a black hole make? Is it a lot or?
It's a lot. I can't give you the exact. See, you haven't told me how many black holes you're considering and what the mass is.
So, I just want to get a sense of the entropy and the amount of entropy.
So you want to compare the entropy in black holes to the entropy in the microwave background radiation. That would be a specific question.
Mm-hmm.
And
yes.
I can answer that question. Maybe someone else can answer it.
Let me phrase it in another way. Now, we know that the entropy of the universe always increases, and we have the talks about the heat death of the universe. And eventually, in the heat death, everything eventually becomes a black hole. So the black hole must increase the entropy. A black hole must have a more entropy than a non-black hole. A star has less entropy than a black hole.
Okay, so if you look at the entropy for a particular amount of matter, then you can maximize that entropy if you form a black hole.
Oh, thank you. That was my question.
Okay. Now, in terms of the heat death, you have to be a little bit careful because we have dark energy. So our universe seems to be accelerating.
Mm-hmm. Thank you so much for that.
Okay, great. Adrian, would you like to ask a question? Please unmute yourself and ask your question.
Sorry, I just asked it when you were gone.
Oh, sorry.
Bill, I took it into my own hands to call on Adrian when you were gone.
Zoe told me, in fact, but I forgot. I was so confused about what had happened. My whole system just fell apart. Computer lost power.
Cronenberg has a question in the chat.
I know, yeah, there are a few questions in the chat. So I don't have the question from Cronenberg because I lost my chat history. So if you did enter a question before I dropped out of the world, please enter.
The question was, why didn't the citation for the Nobel Prize mention the term black hole?
Thanks, Jim.
Robert, do you have a theory? Yeah, Robert, do you have a theory about that? I thought I noticed that as well. I think they were just trying to be very cautious because there have been lots of sort of competing claims about who has the most, best detection of a black hole. Robert, do you have any thoughts?
No, I don't. So it's only for Penrose that black hole was mentioned.
Yeah, I think my guess is that someone must have impressed upon the Nobel Committee that there was some debate. But I think Robert and I have both come down on the side of pretty convinced that there's a supermassive black hole in there.
Okay, maybe I can ask a technical question from the chat. Another question I have is about the tests of GR with the SO2 star. Although it clearly deviates from Newtonian predictions, the fit still seems different than GR prediction. Is this simply explained by experimental uncertainties?
Yeah, I think that I was saying this a little bit in response, I think, to Adrian's question, but I think our primary uncertainty there is actually, even though we know the shape of SO2's orbit better than any other star, I think there are still uncertainties on that. And in particular, the other thing that could be going on is a little bit of precession in the orbit, and that is not well constrained, but will cause additional slight deviations in our ability to constrain the shape of the orbit and understand how it's changing, potentially changing in time. And so there are still slight deviations. I think you're probably looking at that extra dotted line, and we just have fairly large errors, but we'll do better if we can get additional measurements. There's only this one so far.
Okay, maybe we'll go to one last question before we end for today. So the last question is, Professor Brandenberger mentioned that on the joint paper of Hawking and Penrose, one assumption was that the cosmological constant was non-positive. But the Planck team and Lambda CDM model predict a close to zero positive cosmological constant. Is their assumption then incorrect? There seems to be an inconsistency here. Can you comment on this?
Okay, so indeed, if you look at the future, if our universe is dominated today by a cosmological constant, then there's not going to be a singularity in the future. So you see, this is consistent with this caveat of the cosmological constant. Now, if you go backwards in time, then the cosmological constant becomes completely unimportant. The energy of the universe is dominated by regular matter. And so there is a singularity if we go backwards in time.
Okay, thank you. So with that, I think I'll end the last Physical Society Colloquium of the year. Thank you everyone who's joined us via YouTube or via Zoom. We will have more colloquia coming to you live again in January, starting with the new semester. The first colloquium will be given by Renee Hloshek from the Dunlop Institute. So please join us then. Until then, happy holidays, joyeuses fêtes.